today I want to start off by the Euler identity, e to the ix equals to cosine x plus I sine x. If this is the first time seeing this identity, it will look pretty weird because you're seeing an imaginary value in the exponent. Now you've learned in pre-calculus how to take the fractional exponents, how to take negative exponents, but you've never seen exponents with imaginary numbers. And Euler was the first guy to think about such a thing, and he said if you take the imaginary power of the exponent, you're going to get a complex number in this form. So let me try to explain why this is true. Actually, it's just an identity which satisfies good properties. If you recall, when we decided that a to the negative 1 should be 1 over a, it wasn't something that we proved. Rather, this was something that we decided that it will be good because if you define it in this way, then you can extend all the rules of the exponents, basically things like a to the m over a to the n equals to a to the m minus n, without having to worry about whether this is an integer, whether this is a positive number, whether m is bigger than n or anything. See, originally, exponents just mean the following. A to the third means a times a times a. That's all there is. Okay? But once you derive certain rules like this and hope for this to work in all circumstances, then you end up extending exponents to negative powers like this. So that's how the story goes. And here, when it comes to imaginary powers, it's the same kind of logic. There is no definition of taking imaginary powers of an exponent, but there is some rationale for saying that this should be that. Okay, and for this one, that rationale comes from the Taylor series. Now, I know a lot of you forgot the Taylor series, so while I explain this, I will have to do a quick review. Okay. Thankfully, the Taylor series itself won't be on the exams, but trying to remember them will be very helpful because later on you'll be doing it in differential equations, so it is pretty important. Okay. So first thing about Taylor series is that you can express e to the x as 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the 4th third plus 1 over 4th factorial to the x to the 4th plus, and it goes on, it doesn't end. Okay. Now I don't have time to just go over the entire Taylor series, so rather than trying to convince you that such and such formula is true, I'll just try to convince you that this is actually true. Now the first thing I want to say is that if you plug in 1, if you set x equal to 1, the left side is e to the first power. Does anyone remember the value of e? 2.7. It's about 2.7. If you want a few more digits, it's 2.718. Okay. Now, if indeed this equal sign was true, that would mean that if I plug in 1 here, I should be getting this number, right? So let's see if that does give you something like that. So if I set x to be 1, I have 1 plus 1. 1 over 2 factorial. What's a factorial? you multiply all the numbers going down by what, right? 2 factorial means 2 times 1, which is 2. What about 3 factorial? 3 times 2 times 1, so it's 6. What's 4 factorial? 4 times 3 times 2 times 1, so it's 4 times 3 factorial, so it's 24. So if you set x equal to 1, the right side gives you this value. Now what is this? This is 2, 1/2 is 0.5, 1 over 6 is 0.1666. So if you just add up until here, let's see, that's 2.5 is this much plus 0.1666, so that's like 2.66. Okay. And then 1 over 24 is about 0.04. So if you add 0.04 to this one, you're going to get 2.7. It'll be slightly bigger, so and then it'll increase. So already, if you add it up to here, you get a pretty good approximation of the E, which is 2.7. And if you add more and more terms, you will end up with more and more accurate value of E. Now, there is another reason why this is true. So the first reason I'm giving you is basically I'm saying that if you evaluated this value for x equals to 1 or 2 or 3 or anything, and if you evaluate the right side for x equal to 1 or 2 or 3 or anything, and you add up sufficiently many terms, you will see that both sides give you about the same answer. Okay? Actually, if you added infinitely, if you add up all the infinite terms, they're going to be equal. Now, the second reason that I want to give you is that that e to the x has a very special property when it comes to derivatives. What is it? The derivative is same as itself, right? The derivative of e to the x is e to the x, and the only functions that satisfies this property will be just constant multiples of e to the x. In fact, that's what you're going to learn in differential equations next semester. Okay? So that has this special property that if you differentiate d dx, if you differentiate by x, you're going to get e to the x. Let's see what happens to the right side. It better be the same thing. So let's see what happens. What do you get if you differentiate 1? 0. What do you get if you differentiate x? 1. What do you get if you differentiate x squared? 2x, right? But 2x times 1/2 is? This is 1/2, right? 1/2 times 2x, that's x. What do you get if you differentiate x cubed? 3x squared, and 3 times x squared, 1 over 6. So that's basically 1/2, right? 1/2 x squared. This one, 4 comes down, canceling one of the 4s, leaving you with 3 factorial. And so on and so on. I mean, the next term here should be 1 over 5 factorial, 1 over 5 factorial to the x to the 5th power. 5 will come down and cancel it and make it 1 over 4 factorial. So now compare this with the one before. You have 1 here, x here, 1 over 2 x squared, 1 over 2 factorial x squared. Same thing, right? Same thing. Okay. So the right side is also preserving the derivative. So at this point, what else can you do? You're pretty much convinced that this infinite series is in fact doing the exact same thing that e to the x is doing. All right, convinced? Are you convinced that e to the x is this infinite series? Okay. Now, you can do the same kind of work for cosine x and sine x. I did this in detail, but I don't have time to go into the details for this one. I'm just going to write down the infinite series. 1 minus x squared over 2 factorial. Let me write it as 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th. And sine x is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and so on and so on. Let's just write one more time. 1 over 9 factorial x to the... Okay. Again, these identities mean the two things. One is that if you plug in x values, whether x is 0 or 1 or 2 or anything, if you add up sufficiently many terms on the right side, you'll be very close to the actual value on the left side. Okay. So it's if you truncate at a certain point, it will be an approximation of the left side. If you add up infinitely, it will be exactly the same thing. Not only that, the property that if you differentiate sine x, it becomes cosine x, it will be also correct on the right side. If you differentiate this one, you're going to get this one. So that means if you just remember the sine x is Taylor series or Maclaurin series, then you know the cosine. Okay. All right. Now we're going to use the Maclaurin series to argue that this should be what we should have. Okay? Now, how do we do that? Well, this is my plan. I want to take this identity, replace x by ix because that's what I have here. So ix, and then somehow just sort things out and hope that it's same as this one. All good? Okay, so this much is considered as some knowledge that you should already have, something you've already learned. And now we will do the proof. In quotation mark because really this left side is not defined, but I'm trying to say that this is the reasonable definition. All right, so first of all, e to the x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth plus 1 over 6 factorial x to the sixth. Okay, just one more. 1 over 7 factorial x to the 7. And then e to the ix, because I'm replacing x by ix, I should replace every x that I see by ix plus 1 over 2 factorial. Instead of x squared, it will be ix squared, ix to the third, ix to the fourth, ix to the fifth, ix to the sixth, ix to the seventh. Now what is I squared? I squared.
-1.
-1. I cubed.
1.
Negative I. I to the fourth. +1. I to the fifth. I to the sixth. -1. We can do that, right? So you apply all that. We have 1 plus ix plus 1 over 2 factorial, actually with a minus. And this will be minus 1 over 3 factorial ix cubed plus 1 over 4 factorial x to the fourth plus 1 over 5 factorial ix to the fifth minus 1 over 6 factorial x to the 6th plus 1 over 7 factorial I times x to the 7th. Actually, this should be minus, right? And then plus da da da. Now collect the real part and the imaginary part. This is real, that's imaginary, that's real, imaginary, real. Anything that has I in there is imaginary, right? So I'm going to collect all the ones with I's, all the ones without I's. So let's see, 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x to the 6th plus I times what? The ones that have I are x minus 1 over 3 factorial x to the 3rd plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus. Okay, what is this? Cosine. What's this? Sine. Done. So we have the following. That's the reason why we have this identity. All right, let me show you why we want to have this. Now, the consequence is the following. If you have, if you multiply r both sides, then you have r times e to the ix equal to r times cosine x plus I sine x. And writing a complex number in this form is called the Euler form. And if you multiply this out, that will be like, that will just have a regular x component, the real part and the imaginary part if you multiply it out. The multiplied out one will be called the rectangular form. And this one actually has another way of writing, right? This means that the magnitude is r, whereas I used to call this theta. I'm using x. I'm sorry about that. But it's easier to write down as a proof, so that's why I chose x. But this was usually called theta because that's the angle, right? So we can write it as like that. Okay. So in other words, that's the polar form. In other words, if we have r1 angle theta 1, and if I wanted to multiply another number which is r2 theta 2, the first one can be written in Euler form. In what way? Can you tell me how we should write this in Euler form?
R1 plus R2.
No. This only. How do you write this only in this form? R1 e to the what? I theta 1, right? Okay. And then we can rewrite this as R2 e to the I theta 2. Then we immediately have the proof that the angles add and the magnitudes multiply. I told you last time that the proof will be deferred until we do the Euler identity. Yeah. If we have the Euler identity, we can continue on and say R1 times R2 and e to the, what happens to exponents when you multiply with the same base? So the fact that the magnitudes multiply together, whereas the angles add up, has a simple proof if you use the Euler identity. You have a question? Yes?
So R is representing the magnitude?
Yeah, R, if you write it in polar form, this is the magnitude and that's the angle.
So what about R in the Euler form?
Yeah, again,
It's still the magnitude?
yeah, it's the magnitude. So whenever you have a polar form, then you put the magnitude first, and you put the theta here. See, the reason for that is, what's the norm of this? What's the side length of this complex number?
1.
It's 1 because if you square the first and square the second, add them up, you get cosine squared plus sine squared, which is 1, right? So taking the square root of 1 gives you 1. Therefore, the magnitude of this value is 1. If you multiply by r, the magnitude will be r. Now, I'm doing all this assuming that r is positive. So if r is negative, then you may have to change the angle by 180 degrees so it points to the opposite and make this positive. But if r is positive, then r means magnitude, and this is the angle. Any other questions?